Hello everyone, this is Anthony Duarte from Eccentric Engineer, and today we're going to go over Walschaerts valve gear, how to design it, how to make changes to it, and have it still work. We'll go through how it works a little bit. I don't want this to be a SolidWorks tutorial. Everything I'm going to show you, you can do, and you could lay it out in other free softwares, any 2D CAD software, and you could even lay it all out the same way with pen and paper. There'd just be a little bit more math involved. Well, a lot more math involved, but can definitely be done. The point of this, I want to be primarily just to explain the valve gear, show how to lay it out, how adjusting certain lengths affects other things, and just to help anyone out there that might be trying to figure this out and give them some guidance. So I guess first we'll just go over how the motion works, how the valve works. We'll start with outside admission because that's what I've been working on here. I think on the miniature locomotives out there in the hobby, I think the majority of them are outside admission. So let's get to it. I've just noticed actually something's broken here. SolidWorks keeps flipping the crank on me. For outside admission, when the engine's moving forward, the crank is supposed to be leading. On a rod locomotive it'd be the axle, but on this it's the crankshaft. So I have to break some mates to fix that real quick. Okay, there we go. Now it's on the correct side for outside admission. So the reason this is called outside admission is because this whole chamber is filled with steam pressure. When you open the throttle, this is what fills with steam pressure. And that steam comes into the steam port from outside of the valve. On an inside admission valve, steam comes in from the inside of the valve. So it's set up a little bit differently, but the principle is the same. Basically, the whole point of valve gear is to control the motion of this valve so that steam gets admitted to the cylinders at the correct time in the right place. So once we're at the back of the cylinder here and we get to the back and it just barely starts moving forward again, this port is exposed. And that lets steam into the back behind this piston, and it continues to push it forward. It moves and moves happily along, steam still getting emitted. Right there it gets cut off. So now steam's cut off and the expansion of the steam continues to push the piston forward. And actually I should cross-section the valve too here. So right before the end of the stroke, right before the piston gets to the other end, this chamber exposes the steam passage to this center port, which is the exhaust port. So this is when you hear the chuff. This is when all that steam pressure that's in here rushes out through the inside of the valve and out the exhaust port. So now we're at the end of this side, and then once we get past center, just past center, this side opens up. Now this side's exposed and is allowing steam to enter on this side of the piston so it can push it back the other way. And this repeats over and over again, and you get a continuous cycle. Walschaerts is basically broken down into two independent sections that work together. So you have, let's see, these three rods, the union link, combination lever, and the radius rod. This controls your lap and lead. And then your link, eccentric rod, and eccentric crank, these control your forward and reverse valve travel and cutoff. So they add to the motion of the other three components to give you the valve events that you want. So lap and lead, we'll go over this a little bit. I need to move the reverser to center, which I think should be about there. This is when the engine is in neutral. Now you can see, relative to before, how little the valve is moving, and it's actually not even uncovering the ports. It's moving just enough to keep them covered. That is because this engine does not have any lead. So this valve only has lap. Lap is how much longer the valve is than the ports, so that the ports don't come uncovered. Now, if this valve gear design had lead, then that lead would be built into the radius rod, combination lever, and union link design, so that the valve would just barely uncover the outside of the ports. And when that does is right before the piston gets to the end of the stroke, the valve will start to open to sort of cushion the reverse in direction. I believe that's what it's for. That's what I've understood it to be for. If someone knows another reason why lead exists, I'd love to hear your thoughts in the comments. So that's what lap and lead are, and that value is controlled, well, in part by the valve, how much longer it is, and also by these three rods. So that's all the motion that those three rods input to the valve. Then once you start bringing the link down, not the link, excuse me, the reverser, to bring the die block down in the link. So this is only a little bit past center now. Now you can see we get a little bit more travel, and it's actually uncovering the ports. Not very much, but it's enough to move the engine. You wouldn't be able to start an engine, but if you're already moving, this would be just enough steam to keep you going. So you can see the port is open, but it cuts off pretty early. We're maybe not even halfway, or maybe right around halfway through the stroke, and steam's already cut off. With the momentum of the engine and the expansion of steam, it'll keep pushing it forward. And then when you're in full gear, then you can really get some power behind it. Okay, so that's the overview of Walschaerts valve gear. So now let's talk about how to actually design it. I'm going to use this engine as my example since this is what I've been working on. This is basically the Kozo Climax engine. I've been scaling it up to 1 inch, and I've also made some changes. Because of those changes, I had to make modifications to the valve gear, but also since I'm scaling it up and converting it from metric to imperial, I was going to have to make some minor changes anyway, just from the scale conversions. I also adjusted the proportions of these links just to make them look a little bit more like the prototype. I raised the valve stem up, the distance from the valve stem to the cylinder. I made it a little bit taller so that I could make the cylinders look a little bit more prototypical. But all these things, this is why Walschaerts is such a flexible valve gear design, is you can put things pretty much wherever and just design the valve gear around it. But you have to have a fixed set of variables, and it doesn't really matter where you fix them, but you have to fix them somewhere. You have to decide. So if you're working on an engine that's already built, maybe it has some machining errors in it, you need to figure out where things are exactly, so you know that those are your fixed variables that you're designing the valve gear around, or checking, using those to check what the valve gear should be. Let's actually get into it now. When I'm drawing up an engine, I'll just lay out the valve gear in a sketch, basically the way they used to do it in the old days, except I'm doing it on a computer. So a lot of the math is done for me, and I just have to lay it out geometrically. I have a friend that has done this in Fusion 360, which is free software. So I know it's possible. I learned how to draw in SolidWorks, so for me, drawing in Fusion is a huge pain in the butt, but if it's what you learned on and it's what you know, it should probably be pretty easy for you. So I draw 2 circles. This outer circle is my cylinder stroke, which some of these numbers I just remember offhand since I've been working on it. So my cylinder stroke is going to be 1.285 inches. You can put in here whatever it is for your engine. And then this is the throw of the eccentric. This is something that is really not emphasized in our hobby, and I'm not sure why. When the eccentric crank comes up as a topic, people seem to focus on the length and the angle. Either the angle or... So even the way that Kozo has it illustrated in his drawings, he doesn't show the circle of throw of the eccentric, which is the most important thing. He just shows an offset from center line, which I suppose you may be able to set it that way, but I had to kind of work backwards from this to figure out what the circle should be, or something close. It doesn't have to be perfect, but I got it pretty close. I may have just drawn it out and then imposed a circle on it to figure out what the circle is supposed to be, but the radius of travel of the crank is what is important. You can't just go off of a length and an angle and set it there and call it good, because it may not be correct. So these are my two circles, cylinder stroke, eccentric, travel. I'm going to draw another point up here. I don't know exactly, I have to go back and look at what it's supposed to be. This is going to be my fulcrum from my link, and then I'll put another one up here. This is the fulcrum for the reverse arm. It doesn't matter what size they are. It doesn't even really need to be a circle. You could just draw a point, but I like to draw a circle just because it looks nice. I don't remember what this is off the top of my head. I'll have to look that up, ballpark it for right now, and then I'll go back and edit it. And then I like to draw a big construction line that represents the distance from the center line of my crank, or what would be your main rod or main driving rod, to the center line of your cylinders. 2 points to represent the center lines of your valve and your main cylinder bore. The most important one is the center line of your valve. You don't really need the center line of your cylinder bore, but I like to just put it on there anyway. Okay, so now I've imported all the correct dimensions, but I just realized that I made the same mistake that I made the first time I did this. So I made this vertical, forgetting that the climax engine is on an incline. So this actually needs to be moved forward by the same angle that the same angle as the climax engine, which is 22.5 degrees. Oh, not that way. About 90 minus 22.5. There we go. And I don't want these construction lines buggering this up, so I'll just do this. Okay. All right. Now, that's step one. So these are my fixed points. These are things that I know where these go in the engine. These are points that you could measure off an existing locomotive. It might be with some difficulty. The thing that you want to be most precise about measuring, if you are doing it that way, is the position of your link fulcrum. This point right here is very, 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 very important. If this moves at all, it changes everything. That's absolutely critical to know exactly where that is. Okay, so we have our fulcrum points, stroke dimensions. So I'm just going to draw some lines to represent the rod lengths. So this is going to represent the main rod, which is 4.285. This is the drop down off the crosshead, which is 1 1/8. If your design has a drop down and an offset, you need to make sure to include that. Not very many do, but they're out there. And then when I draw the lines for the union link and the combination lever, I make sure to draw them at an angle so that they don't snap automatically to being either horizontal or vertical. The top of the combination lever needs to be made horizontal with the center line of your valve. If this is for piston valve or inside admission, you need to make the middle point of your combination lever the point that is horizontal with your valve center line. From our link fulcrum point, we're going to draw the radius rod, which is 2.463. Got a little mad at me there. Just swing that around. Just put it somewhere that looks kind of close to where it'll end up being. But this has to be to this point because this is the neutral point. So this is the point at which the link inputs 0 motion to the radius rod. So this is purely the motion of the lap and lead introduced from these 3 rods and the crosshead. So I'm drawing the radius rod, combination lever, and union link at the front and back of the stroke. And I'm going to make these lengths all equal to each other, since theoretically it's the same rod, just in a different position. So the 2 top are going to be equal to each other, the bottom half of the combination levers equal to each other, and the 2 union link lines are equal to each other. Instead of drawing another line for the main rod, I'm just going to put a dimension here for the stroke. So now these 2 points are fixed as the back and front of the stroke. We'll draw another radius rod in here because it may not be They probably won't be exactly on top of each other. So now we're getting pretty close. I want to make the union link the same. I don't want to make any changes to the union link dimension. So that's going to end up being a fixed variable. And the reason for that on this particular engine is because the union link gets very close to the back of the crosshead guide flange. And I want to make sure I still have room for a stud and a nut or a bolt, whatever I decide to do. So I don't want to risk making this any longer than it needs to be. So we'll keep this the same. If I remember correctly, it's 0.803. 0.803. Okay, so that's a fixed variable. Now if I just kind of drag this around and play with it, which I think this is a little harder to do on Fusion, but I should be able to see, yeah. So I can see what's flexible, and you can see the distance between these 2 points is a number that I can change a lot, which in turn affects the proportions of these two halves of the combination lever. So this distance here, this is going to be your lap plus lead times 2. So on this engine, our lap is 0.0535 plus 0 lead. There's no lead, so I don't have to worry about it, times 2. But if you did have lead, say there was 10 thousandths of lead, then you would want to add that in as well, and then multiply that total number by 2. Because that 2 times the lap plus lead is the total travel that you want introduced from this combination of rods. So we're going to go 0.535 times 2, which should be 0.107. Yep. Now what's variable? Interesting. So at this point, I would make this the same as your print, or make it a distance that you know will clear the valve crosshead and the round end of the radius rod have to both fit in this small space. So if you know how much clearance you need, put that in. But really, I mean, you can set it to whatever works. You should probably consider the union link, because when it swings, it'll either swing up or it might swing down. So I like to put it somewhere where it'll be even. So that's what I wound up making this. The important thing here is that you're getting the correct amount of travel, and that there's, nothing too crazy happening here. There's a rule of thumb that the total travel of the combination lever should not exceed 60 degrees, or that the total angle of the travel should not exceed 60 degrees, right? Yeah, it's at 34.2 degrees. So we're fine there. Okay, so now this is done. This is what it needs to be. This is what it has to be for this engine. Now, there is still flexibility here. Say, if you're designing the engine and you realize the link's too high, it needs to be a 1/16 of an inch lower or something, you can come back and just lower it. I actually raised mine. I raised mine up, I think, 1/8 of an inch to accommodate for the fact that I made the valve center line a little bit higher. I had to increase the length of the fulcrum, the height of the fulcrum. So if I needed to drop it back down for some reason, it changes the lengths appropriately. So it would have changed this length a little bit. Let's see, it's 182 and 3/10 right now. So now if I move it back to where it was, and now it's 0.182, it's hardly even smaller, but it did change it to make the geometry work out and have everything still be equal. So there's tons of flexibility with this valve gear. Okay, now the link has to be next. You may notice that the radius rod here is at a slight incline. It's at a slight angle. That's perfectly okay. I almost always see them lower at a slight angle. The reason you can't draw the link until this is designed is because this angle has to be taken into consideration. The radius of your link is going to be equal to the length of your radius rod. It was 2.463. I like to make this segment midpoint with the fulcrum just to make it nice. And the way I make the offset foot is with a series of center lines. Draw a center line from the center point of the arc to the middle, perpendicular line down and over. I'm going to have to check what these numbers are supposed to be. So Our offset here is 268, and it comes down 878. Okay, and we want this to be on this angle. We do have an issue here, slight issue, since it's not perfect. They don't end up exactly in the same spot. You could split the difference. It's probably what I would do. This is only a 0.002 difference here, but I drew a little construction line between those 2 points and put a little point right in the middle of that line, and I'll make that point coincident with this line here. So that will put the angle, you can see this is at an angle that's perpendicular to the angle of the radius rod when it's in neutral. And I split the difference. It's so minor, you would never see that, but just for the sake of trying to make this as good as possible here. Now we've fixed the attachment point to our link by setting this angle, this little backset angle here. And now we can draw our eccentric and eccentric rod, which has to be defined by the radius of travel. So since this is outside admission, the crank has to go this way. On a piston valve engine, it would be this way, but it's going to be this way for slide valve outside admission. So we're going to draw a line to represent our eccentric crank and its attachment point on the radius of travel. And then we're going to draw a line to represent our eccentric rod. And then we're going to do the same thing on the back side of the stroke and connect it to that same point, because this is where the link has to be at both the front and back of the stroke. The proportions of these two rods has to be such that at the front and back of the stroke, it puts this point in the same position, at the same angle. So this is very easy to do, at least in CAD. You can figure this out on paper by doing just a little bit of triangle geometry, get out your Pythagorean theorem. But all we have to do is make these two segments that represent the crank equal, and make these two segments that represent the eccentric rod equal. Done. So now any change I make, if I need to change this angle, in fact, I'll show you. If I needed to change the angle, these change with it. So you can see how those are changing. I mean, this is grossly exaggerated, obviously, but you can get a very, very precise calculation for what those rod lengths are supposed to be. So we'll set this back. We are almost done. We can say with pretty good confidence that so far everything we've drawn here is correct. We do have to take in consideration the radius rod lifting link and the back set off the radius rod. I have seen on some forums before people saying that these don't have a great impact on the valve gear, but that is extremely not true. It is true in neutral. It's mostly true at low cutoffs, but when you get into full gear travel, you are going to have a very bad time if these lengths are not correct. Because what's going to happen if these aren't correct is you're going to have very, very uneven cutoff from the front and back end of the stroke. You might have 80% cutoff on the front end of the stroke and like 65% cutoff on the back end of the stroke. If your engine is square to the world, you're going to have uneven chuffs. You'll end up having a strong chuff in the front and a weak chuff in the back, or vice versa. And that's because this link affects the way that the radius rod swings inside the expansion link. So that's the next part of the puzzle. So from here, we'll do another sketch on top of this. We'll sketch it out with the radius rod in gear. And there's always going to be a little bit of error. On mine, what I actually wound up with, I think I have about a 1.5% difference in full gear between my cutoff at the front and the back. So, the valve travels just slightly further in one direction. And it's the same thing on full-size locomotives. I was looking at a chart just last night. One of the British engines, I don't remember which one, had in full forward gear, it had like 3% difference from forward to back on the cutoff. So now we need to draw the valve gear in the middle of the stroke. The middle of the stroke is not super valuable. information for timing a locomotive, but at the middle of the stroke is where, when you're in full gear, that's when the link is at the front of its stroke, because its cycle is 90 degrees off from the main crank pin. So when the crank pin's halfway through its travel, the link is at the end of its travel. And that's what we're worried about with cutoff. So, well, not exactly with cutoff, but as far as how far the valve is able to travel in either direction. So let's just start putting some stuff on here and just throw some lines on. This is the trick to getting fast at drawing in CAD, by the way, is don't worry about drawing it correctly. Just throw the lines on there and then go back, put some restrictions on the geometry, and then go back and put your dimensions in. It is so much faster. We actually don't need to put dimensions. We can make, since we have all this stuff in the background, we can just copy over. I'm going to grab the main rod line and my new main rod line and just make them equal. Same with the union link and the two segments of the combination lever and the radius rod. And now we are not going to put this at the center of the fulcrum. We're going to have it down here somewhere. So one thing you need to decide is where you want this to be when you're down in full gear. On this engine, it wound up being, I wound up making this 85 degrees, just purely based on looking at pictures and videos of climaxes. When it was in full gear, the radius arm was like maybe just slightly lower than horizontal. You know, this would actually be more like closer to that, right? Because it's at an angle. But okay, so now we have this. We don't know exactly what we want these to be yet. And despite what some people think, it does have a significant impact. I made a mistake. Forgive me. We have to redraw the link because right now it's at the neutral angle. So we're going to do the same thing as before, but now I don't have to put the dimensions back in. Yay. Another thing we need to do actually, because we want this in the middle of the stroke, I'm going to make this. I'm going to type out our stroke, 1.285 divided by 2. Just kidding. Why won't it let me do that? Okay, maybe I can do it now. 1.285. There we go. It's important to define the mid-stroke this way based off of the crosshead position, because if you were to, say, do it off the main rod position and make this point vertical to the center of your main rod or crankshaft, whatever it is, that would not actually be halfway through the stroke, because as you can see here, the main rod is actually slightly just past center. Just know that the halfway point has to be defined by the crosshead and not the percentage of travel on this arc. Now that we know where our main rod is, when we're halfway through the stroke, we can put our eccentric geometry in here, our eccentric engineered geometry, you might say. Okay. So now with this information, now we know where our link is. Now, in full gear, instead of being connected to the fulcrum, it's going to be on here somewhere. And then we have our back set here. Make this collinear since it's the same rod. Okay, so now we don't know what this needs to be just yet. We need to draw the other side first. Actually, we need to draw the link again. We'll draw another link on here. You know what? To make this a little bit cleaner, let's do this. So we need to draw another link, and this is going to start to get messy. So we'll do this in its own sketch. I mean, we'll make a separate sketch for the rest of the stuff that we're drawing here, just to keep it a little bit cleaner. It's just doing what we've already done. So mid-stroke is going to be the same. On the flip side, the crosshead's still going to be in the middle. So all we have to do is draw a line to represent our eccentric motion, and it's going to be at the same point vertically. So we can make this point vertical to the main rod at the bottom, make the eccentrics equal, make the rods equal, and I need to set the radius. There we go. So now we have our link position in neutral, we have our link position in full forward and full reverse. This is of the link's travel. Okay, we'll keep that in a separate sketch just to keep things looking a little cleaner. We're going to draw the union link and combination lever off of here. Radius rod is going to connect down on the link, and then we have our reversing stuff. Put this back to 85. For now, we just need to get the geometry on there. Put all our relations in here. This needs to be horizontal. These lines need to be the same length. Make these equal. Make these equal. What's missing here? I think that's it. And we're going to do the same thing again, and it's going to come off the same point. We're going to draw another radius rod, but this one's connecting to the back of the link that's on the back end of its stroke. These will connect to the same point here. Make the radius rods equal. They're already equal. We want to make these back set lines equal to each other. And we want to make the lifting link equal to each other. We'll fix this line. It's a good idea to make one of these a fixed variable, whatever you know to be, say for example, if you know what this is according to the print for your locomotive, or this, you can see how important these lengths are. They make a big difference if they're not set correctly. So what I want to do, we want to fix one of them. So it's going to be a bottom limit for the link, how far down it can actually travel. So we want to set it for as far forward as possible. The back of the stroke is where the link is lowest. That's this one. And you can see it's true on here too. I mean, it'd have to be really long for it to switch and for the front to be the lower one. So the back is slightly lower, and you can look based on the tall opening of your link in combination with how tall your link block is, how far down it can travel before it starts to interfere. So now from fulcrum to the back, we decided on 0.347. That's as far down as we can allow it to go in the back of the stroke. So now that has fully defined our location here. You can see we have a little issue. This illustrates probably most clearly why these lengths matter, because this is how you get uneven cutoff between the front and back of your stroke. What I'm going to do here is I'm going to draw a line from here to here and from here to here, because I know that our neutral swing, the swing of our combination lever in neutral, is definitely even travel over the center of the ports. So I have these two construction lines. I'm going to make them equal to each other. So that forces our valve travel to be equal over the ports at the front and back of our full forward travel. So now we have our segments, and we still have some flexibility here. You know, if you decide you want this to change, you can see what it affects. So I made the decision to make this as short as possible. Not quite as possible, but a lot shorter. I made it 1/2 inch because it just, looking at photographs of climaxes, the reversing arm was pretty close to the back of the link. I made this tighter. It was like, I don't remember exactly what it was, but it was quite a bit longer. I think it was around 0.8. So I tucked it up to 1/2 inch. And, you know, if you're not happy with this length, you can change the angle, and, you know, you can play with it this way, just, you know, somewhere where you like it. All these positions are going to work. Well, I mean, not exactly. This would not work, but, you know, anything within, you know, reasonable length is going to work. This is what I mean when I say that Walschaerts is a very flexible design. I'll put this back at 85 though, because that's where I put it. I don't think these dimensions are exactly what I wound up doing. So let's see what this length is. I made this 1 3/8. So let's just port that number over. Okay, now we got 1 3/8 there. We can look at these measurements now. We got 0.8528, 1/2 inch there, because that's what I set it to. In order to make this 1 3/8, I had to delete my angle dimension, my 5 degrees. So this matches what I actually have the 3D model at. So it's actually not, it's only like 2 or 3 degrees. That was 347. Well, that's our valve gear. This will be a very square valve gear with very, very close to even cutoff in full forward and in reverse. You don't have to do anything again in reverse if you do all this correctly. So what I'm going to do is I'm going to, steam's entering into the back and it cuts off there. So what I want to do is just put a temporary relationship in here where those meet. That is going to be cut off. That's exactly the cutoff point. So now I'll draw a center line, make it infinite length, because why not? If this engine wasn't inclined, I wouldn't have to draw this line, but it is. And now I'm going to draw a semicircle from the crank to the back of the stroke. And it tells me here how many degrees that arc is. Yeah, 138.36. 138.36 degrees. So that's how many degrees the crank has traveled before steam emission gets cut off. So I'm going to divide that by 180 degrees, half a circle. So that gives me 76.8% cut off at this point in the gear. So I'm just going to write that down. And now we're going to go to cut off on the other side right here. Mate those faces. Okay, the moment of truth. Is your heart racing? Because mine is. Have I just scammed you for the last however long this video is? 134. Which sounds like a lot, but let's do the math. 134.147 divided by 180. 74.5%. We'll go, yeah, 0.52. 76.86 minus 74.52. So 2.34% difference, which is completely acceptable. Like I said, full-size engines were more than that. Realistically, I mean, yeah, it's 2% off, but that's not something you would ever notice. And you wouldn't, like, if you were timing it by eye, actually, you wouldn't time it in forward anyway. You would time it in neutral. But 2%, 2.3% difference, you're not going to notice that in the evenness of the chuffs. You're not going to notice that in any like lurching of, you know, one stroke being more powerful than the other. That's going to be really even, crisp, square. That difference does get worse the further down you go. The difference in cutoff gets better the closer you get to neutral. I said I was going to go over inside admission, but for the sake of this being a timely video, maybe I'll do a second video later that just quickly goes over inside admission. You know, hopefully if you know a lot about Walschaerts valve gear, I hope you learned something. If you don't know anything about Walschaerts gear or even trains, I hope this, I hope you learned something too. I'm definitely going to make more videos in the future about other appliances and how they work, and go do a little bit deeper dives into some of this stuff. So hope you enjoyed. Thanks for watching. Thanks for sticking it out to the end if you did, and we'll see you next time.